In this installment, we are going to look at explosions with a focus on the formulas and the related concepts, and we're talking about conservation of momentum. And just to remind ourselves, we have three different types of interactions when it comes to momentum. We have explosions, we have sticky collisions, and we have bouncy collisions. And so today in this installment, we're looking at explosions in detail. Well, we are starting from this premise that the law of conservation of momentum, which says the total momentum of the system remains constant. The initial momentum equals the instantaneous momentum. At every moment in time, the momentum is constant. So we'll start out with a particle like so, and it's at rest. So P0 equals 0, V equals 0. And that particle then is going to explode into two pieces. Piece 1 and piece 2, where this is our negative direction, this is our positive direction. So if we were to look at our momentum here, what we'd see is that we have the momentum of 1, this particle, and we have momentum of 2. Well, in the beginning we have 0 momentum, but clearly after the explosion, particle 1 has momentum and particle 2 has momentum. And the issue that comes to be in this case, how can we create momentum? Well, we're not actually creating momentum. It turns out that the momentum of the first particle has a negative velocity, and the second particle has a positive velocity. So if P0 equals P, the two particles, we have 0 momentum before, and afterward we have momentum of particle 1 and momentum of particle 2. So those momenta are equal and opposite to each other. Equal, and the negative sign means opposite directions. So this is our standing relationship. They are equal and opposite to the other, and that's because one of them has an opposite direction of velocity. So when we add up these two momenta, they add up to 0. So whatever the momentum of 1 is, the momentum of 2 is exactly the same magnitude, but opposite in direction. So that's what that means. And we, of course, can then put M1V1 equals an opposite to M2V2. So that's a nice little example of what happens. We have two particles, but many of you may be saying, but wait a minute. Explosions don't involve just two particles. Maybe there's 3 particles that it explodes into. So let's consider the case where there are 3 particles that are exploded, that it explodes into. And we have particle 1, particle 2, and particle 3. And so we have particle 1 going that way, which is the negative direction, and particle 3 going in this direction, which is the positive direction. Well, particle 2 could be stationary, but let's imagine that it's actually moving to the right as well. So we have the total momentum of the system, which is 0 beforehand, and afterward we have the momentum of 1, 2, and 3. And we can see that these two have momentum that's opposite to this momentum. So solving algebraically, we get P1 is equal and opposite to the momentum of P2 and P3. The sum of these two, which is the right side, are equal and opposite to those on the left side. So then you could see we could extend this to any number of particles, to P to the n. It could be 10, 20, 50, 100, 1,000, a million pieces, and we would just be adding terms there. If we had, say, 10 particles on the right and 5 on the left, then there would be 5 terms on the left and 10 terms on the right. But all of them moving in one direction will have equal and opposite momentum to the particle in the other direction. So this is our basic formula, and the concept that it represents is that the momentum of one particle, one direction, is equal and opposite to the momentum in the other direction. So let's now apply this explosion to 3 fundamental concepts that we want to relate to momentum. And let's